Hello fellow skeptics, I'm Luther Name, and this is the 7th video in a series addressing the broad topic of, is something wrong with modern physics, and if so, what? And if there is something wrong, can we fix it? Now, because of the holidays and some other intervening events, why these videos have been delayed, so I'm going to generate a couple and post them in fairly quick succession here, because 7 and 8 are highly interrelated. Part of the delay in putting them together was that the topics are very tightly wound together. So what I'm going to do is begin to get to the underpinnings of why special relativity is wrong. To do that, I have to introduce some physics that, because of the way the whole issue of special relativity has been addressed over the last 100 years, there's physics that people are aware of, but they're just not they're not thinking it through in terms of what the consequences are. The fundamental one, quite frankly, is a topic that is going to make your eyes glaze over. It's the issue of inertial versus non-inertial propagation. Now, most people would not even be aware of that. Most scientists would, or they've heard the word inertial, and so anyone who with a technical background may think that they understand what inertial is, but I'm not sure that they know what non-inertial is. And the fact is that electromagnetic radiation propagates non-inertially, whereas mass and matter propagate inertially. And there's a fundamental difference in the way these propagation events occur and what they look like. And it's been an abject failure of the physics community not to recognize these differences. And it's these differences that basically undermine what we believe are the foundations of special relativity. So what I'm going to do is provide a description of what inertial and non-inertial propagation is and how it impacts the way we have developed our ideas of special relativity. Fundamental experiment that drove many of the ideas that underlie special relativity is the Michelson-Morley experiment. Michelson invented an interferometer that uses light. Now, in the late 1800s, he performed an experiment, and the sources of light and the way the experiment was conducted were very primitive compared to what we're able to accomplish in modern days. But the basis for the Michelson-Morley experiment and the description of that experiment uses physics that's just wrong. It was wrong at the time that it was used to describe what should be seen in the experiment, and it has continued to be copied by people who haven't done any independent research on it. And so the same basic descriptions and diagrams and analytical approaches are the same as they were 130, 140 years ago when the Michelson-Morley experiment was performed. Never looked into it, never questioned it. Yet it's one of these things where they know that there is a difference, and they know, the physicists we're talking about here, they know there's a difference, but they simply haven't bothered to go back and do it. Everything's a copy of what was done by the giants of the time. And they were very clever people, but they didn't know enough. And they didn't, and in fact, I will ask anyone out there who knows when the distinctions between inertial and non-inertial propagation was something that was formally acknowledged, and when it became something that people even thought of it. It's hard to believe, but I don't think that anybody really thinks anything about it. because most of the discussions and descriptions used for describing the experiments and the results that gave rise to things like the equations for the contraction of length in the direction of motion or time dilation use inertial descriptions to describe non-inertial phenomena or events. So what I'm going to do is I'm going to use this video as a basis for laying the groundwork for questioning whether or not we truly understand what we're looking at when we make measurements, when we make these diagrams, when we look at things like simultaneity and we draw these scenarios and we make these pictures and show the propagation and what we're trying. I don't think we have a clue. Haven't had for 100 years, and nobody's given any thought to it. It was one of the types of topics that ultimately drove me out of academic physics, because these descriptions were clearly wrong, and yet they were baked into our textbooks and into the curricula, and they were wrong. Anybody who'd given any thought to it would know that they were wrong. So with that, what I'm going to do is I'm going to get into the discussions of inertial versus non-inertial, and then from there, the next video, the 8th one in the series, will be a direct dive into the fundamental underpinnings of what special relativity is all about. So we're going to start here with a diagram that will play an important role in the next video. But keep in mind that this is what we're leading to when we talk about inertial and non-inertial propagation. This is a schematic of the Michelson-Morley experiment, where you have a beam of light. It comes in and hits a beam splitter. Part of it is deflected vertically, and part of it passes through to a mirror. These mirrors then reflect the light back through to a detector. Usually it was an eyeball in the old days. And this beam comes back, hits off the backside of this beam splitter and mixes at the detector with the light that has gone vertically and come back down. Now, I'm not going to get into the details of what this is, but this is a diagram that goes all the way back to the way Lorentz visualized the workings of the Michelson interferometer, and basically how the Michelson-Morley experiment was configured. So we'll leave it here, but this is a particular description that we'll get back to and plays an important role in terms of, in the next video, in terms of identifying why special relativity is in fact incorrect. So what I want to do is describe what the beam of light would look like. Now, light is called non-inertial, and what that means is this. If you compare these two circumstances, and by the way, you could, this is just the vertical axis of the Michelson interferometer. You could see that the horizontal axis is just a depiction of what was shown in the thought experiment that Einstein put in his 1905 paper. So combining the two, you have then the light paths, or the behavior that you would get within a Michelson-Morley or Michelson interferometer. In this particular case, a pulse of light is launched at time 0, and what happens is, because the light is non-inertial, it has no characteristics of the velocity that the source may have or the apparatus may have. The light beam goes in the direction it's initially launched, and it goes vertical, and what happens is the apparatus moves horizontally out from under the beam so that the beam seems to be displaced a distance from where it would normally be, and then it's reflected back up, and again, that's just the apparent direction the light would go. If you were to fill this apparatus with smoke, again, this is what you would see. But what's really happening? The light beam is always only traveling vertically between the two locations, between the initiation point and the mirror. And if you had two mirrors, it would be bouncing vertically, but because of the motion, it would appear as if it were moving on a diagonal. Now that's what happens with non-inertial motion. With inertial motion, what happens is if you're in an apparatus, you have the physical object like a ball, and if you were, say, in a spaceship, and the capsule is moving with velocity in this direction, and somebody inside takes a ball and shoves it towards a wall, it has that velocity of the whole apparatus, and it keeps that velocity. And so what happens is, if you're in the apparatus, you would see it just travel straight down to the wall and bounce off and come straight back. It would not deviate. That's because it's inertial. It contains the inertial motion associated with the velocity of the system. That's the distinction between the two. Now, this is, again, if we take a look at the horizontal and then the vertical aspects of the Michelson-Morley interferometer, you can see that this one duplicates what you would expect from that initial thought experiment depicted by Einstein, and this is what the vertical component of light movement would be. But notice that even though it's shown as moving in this direction, and that's an optical illusion, the velocity of light and its path is really always straight up and down, moving with c. It does not move velocity c in this direction. It would move with a slightly larger velocity because it's traveling the same distance, a greater distance in that time. It's an optical illusion. The light does not actually travel along this path with the speed of light. So here's what we really have that's going on here. This is another depiction of the same thing. The light goes in a horizontal direction. It's as we've shown, it just goes down and back because the motion is along this particular axis. I've shown them separated here just so that they don't get mixed. But what actually happens in the vertical direction, because the apparatus is moving in this direction, the blue line is actually a depiction of the offset that would have occurred by the actual horizontal motion of the apparatus itself. So this is just to reiterate what the difference is between the inertial and inertial, or non-inertial and inertial motion. So how would we actually measure that? If you're in the apparatus and you have some smoke, if you were to say have a physical object that's falling with some velocity v fall, this is just a detector, a radar of some sort, and I'm over here at some offset angle and I'm looking at it, I would be measuring it with some sort of an apparatus that could measure the distance as a thing falls. And I know how fast I'm moving, and I know that as I mark the time, how far I've moved. And so at each instant here, this would be a depiction of what I'm actually seeing. And when I look at that, what I get is, even though this is an inertial object, in this case, because the observer is moving and the apparatus is not moving, what you get then is a measurement that looks like this. It looks like it's non-inertial. It looks like what happens is that this physical object is moving non-inertially, even though it is moving inertially. That's what I would measure its motion as being. I could tell it wasn't something like a beam of light and was something physical like a spheroid or a ball, because I could measure the speed of the thing as it's falling. And so I would know that I'm not dealing with actual pulse of light. So there's a tendency to mix all of these aspects of viewing things up, between inertial and non-inertial, between what's displaced and what's not displaced. Now, simultaneity uses some of these same ideas, but let's see exactly how it works out. This is one of the thought experiments that Einstein came up with
In this particular instance, this would be a light source outside of a train, and this is an observer in the center of the train car. And these are two sources of light that are synchronized so that they strobe or flash at exactly the same moment. Einstein uses lightning flashes. What happens is that the person at the center between the two would see the two as simultaneous. If this moving observer is just opposite the stationary observer at the time these strobes occur, in the time the two light pulses would not reach this observer until he's moved off a certain distance given by the time it takes for the pulses to arrive. And you can see that because the distances are greater and because the speed of light is constant for each path length, the appearance would be that they are not simultaneous. This is a trivial example. This is something that's used over and over again in trying to model things in various scenarios and detecting objects, doing signal intelligence, military, even in practical tracking algorithms used for airports and what have you. This is a trivial example, and it has nothing to do with simultaneity per se. It has everything to do with the round trip or travel times of pulses of light, given that observers are not at the same place and that one's moving relative to another. In a practical sense, something that crops up, and this is an example of a real piece of equipment. On an aircraft, we have a side-looking radar. That radar shines a beam perpendicular. This beam travels straight out, even though this aircraft is moving along its path. That light beam continues along its own path because it's non-inertial. It has no component of motion in the horizontal direction that's along the direction of motion of the aircraft. It travels out, the pulse travels to a target, some point out there, and then there's radiation scattered back from it and reaches back to the aircraft and is received there after a certain time that the aircraft is flown. When you go through and you take a look at the round trip times and the distances, and because the speed of light is constant on each of these paths, this is the only speed that is less than the speed of light, you can come up with a variety of calculations. For instance, the time for a pulse to get to the target is given by this expression relative to the aircraft's time of motion between the pulse going out and the pulse being received back, and you wind up with this kind of a characteristic where beta is again the velocity of the aircraft over c, the speed of light. These terms show up all the time when you're doing these round trip time types of experiments and measurements. It has nothing to do with the rate of time. It has everything to do with elapsed time. And it was a confusion of the people during the fin de siegue period in not understanding fully what the ramifications were of something having a constant speed of light. They confused the issue, and they confused the issue in terms of deciding or describing apparatus like the Michelson-Morley interferometer, or it's really the Michelson interferometer. It was a Michelson-Morley experiment.
In the next video, the 8th video, I'll be doing a deep dive into the Michelson-Morley experiment and the description of the Michelson interferometer. Now, I had not originally intended to do that particular deep dive. In fact, this video that you're watching now, number 7, was actually prepared after I had done the work that I'll be showing in the next video, the 8th video, because I realized that there were some subtleties that almost nobody's aware of. And as a result, I had to prepare this video to lay the groundwork for what I would call the big reveal in the next one, in the Michelson interferometer. It was something that always troubled me, but I could never put my finger on what the issues were. This video sets the stage for now being able to describe what happened in terms of the fundamental experiments that were used to drive the ideas behind special relativity. And what I found was that the Michelson-Morley experiment has been totally mischaracterized, and the findings have been mischaracterized. And that's going to be the topic of the next video. Now, I'm Luther Name. Thank you for watching. Please leave some comments, and I'll talk to you in the next video.